Hey everybody, thank you. Welcome to the stream. I'm just starting with some stuff I've been working on. I still have no idea why I'm getting these node not found errors. I'm guessing there's it's actually I don't know. maybe it's trying to free, some pattern is trying to free a node that is already freed by its internal envelope. I'm not sure. Can you guys hear me okay, by the way? How's the audio quality today? Awesome. Thank you. Appreciate that. Alright, let's add some more stuff here. I think the node not found errors are the result of the language trying to free a node that doesn't exist. So I think it's not a set command or failing to create a synth. I think it's just, I should track that down though, because I don't like it. I don't like that error. Yeah, it reminds me of Autechre too, and maybe some of like Aphex Twin's selected ambient works, just tones with lots of reverb. I have 3 things here, don't I? 1, 2, 3. Oh wow, that's not how you spell pbind-f. So yeah, hey everybody, welcome. How's everybody doing today? Oh my god, yeah, there are. I know it's kind of a nightmare just scrolling up and down. This is not the right way to do it. Like if I were actually doing some formal performance, I would probably not do it this way. No, it does not seem like the right way to do it. You can just make a GUI yourself. Yeah, I'm not gonna try to make one right now, I guess, but there are quarks. I think there probably a lot of people have created various graphical interfaces for managing patterns. There might even be, I have a vague recollection, pdef.gui gives you this. Oh wow, look at that. Yeah, okay, so I've never actually used this. I've seen it every now and then. And this is a class, it's a method for the class pdef that gives you a GUI of all of the patterns currently contained in the global dictionary. And I don't know anything beyond that. I wonder if there's we can look that up. Undocumented class methods. So we can't immediately see any more information, but what I would do is I'd probably just start tinkering around with this and seeing what happens. And I'm of the school of thought where I would want to do it myself. I'll figure out how the piece is going to go and then make my own, depending on my needs, stuff like that. So anyway, but that's a little nugget of wisdom that might be useful to some of you out there watching. Yeah. Okay, so today I was going to talk about waveshaping, wavetable synthesis, and ways you can do that in SuperCollider. Yeah, no problem. So this Kick Shaper 0, is it going to run? Yeah. I changed a lot of these numbers. This is all wavetable synthesis. See if I can. And what it's doing is it's picking randomly from 3 synth defs. K-shape 0, 1, and 2. And I added those recently. And K is something that's been on stream before. It is just a synthesized kick drum, and it's very simple. The sound source is a sine wave, and there's a frequency envelope. So that just sounds like this. It's amazing what you can do with just sine waves. And then I made 3 additional synth defs, which are almost the exact same thing. The difference is that the source, the one waveform being used is a low frequency sawtooth, so it's just a simple linear ramp going from -1 to +1, I think. Or is it 0 to 1? No, it's -1 to +1. So it's bipolar. And that's being used as the index in a shaper unit generator reading through a wavetable. So the wavetable is an argument. It's a buffer number, basically. And that's the only variation here. K-shape 1, I do the same thing, except then I pass it through a resonant low-pass filter. In K-shape 2, I use the wave shaper, pass it through a resonant low-pass filter, and then run it through the shaper again. So the result of this filtered wave-shaped process is then used as an index into the wavetable a second time. So this pattern is in choosing from one of these 3 synthefs, along with randomizing a whole bunch of other arguments, and yeah, that's the result. So the wavetable, I've added a new section at the beginning when we first boot the server. Tilde WT is an empty dictionary. Excuse me. And then we add a buffer. It's ultimately a buffer, and we're using the load collection method to basically turn an envelope into a signal, normalize it, and then we convert that signal to a wavetable. And then we add that. So that becomes a buffer. We load that wavetable collection into a buffer and store it in our dictionary WT at the index symbol 0. So if I were to just take a look at this here, you know what? Let's just copy this into a new document and simplify it a little bit. So if we dot plot this, it is what the comment said it was, the 20 segment random envelope. So we have random levels between -1 and +1. The times are exponentially chosen, randomly chosen with an exponential distribution between 0.01 seconds and 2 seconds. And the curves are also random. So some of the curves are, sort of hilly, and others are more linear. And so we take that env and we turn it into a signal. And what that does, so E is now a, probably shouldn't have called it E. I just didn't want to call it S because that's the local server. And let's stop with this tempo clock, shall we? We don't need that anymore. So E is now a signal, and I'll go over this starting from absolutely nothing. I'm just sort of showing what I've done in my sketches file. And signals are, I believe they're subclasses of collection. Is that right? Oh yeah. So it inherits from arrayed collection, or array as we know it, and so there's collection is one of the bigger subclasses. It has a lot of stuff. Array, dictionary, signal is also a collection. It's very, very common. So if it's a collection, I believe that means we can plot it. And here it is. It looks exactly the same because, well, maybe we generated a second time. Is that why it's different? Let's do it this way. So we go. Actually, let's e.plot. E equals e.as signal, and then e.plot. So this should give us 2 plots, 1 and 2. And I'll try to remember not to hide stuff behind the chat window. So they're exactly the same. One of these is a plot of an instance of the env class, and the other one is a plot of an instance of the signal class. And so they're very similar. They're exactly identical. They're just different classes. And then what we do is we say e e.as wavetable no wrap. And then if we plot this, it looks sort of similar, but it's also different. Right, so this is we've now converted the signal to a wavetable. And that's a special format that SuperCollider uses, which is more efficient because the difference between successive samples is those values are also stored in the buffer. But I'm sort of getting ahead of myself here. Let's just start back at nothing here, and I'm going to open my cheat sheet so I don't get too lost here. Okay. So, right. So we'll start with let's make a just start with this. What's the best way to do this? How did I do it down here? I think I just used sig and tilde w. Okay. So we wanted to start with a signal because we need to convert a signal into a wavetable format because that's what shaper.ar needs. So I think what we can do is we can just say new clear. And if we're going to take a signal and eventually turn it into a wavetable, then we need a very specific number of samples. Specifically, it's got to be a power of 2 plus 1. So 512 is a power of 2, so we're going to make this a signal, an instance of signal, which has 513 values in it, and they're all 0. And I mean, there are various, I think there's probably a fill method that gets inherited here. So we could also do something like this and fill it, with values of 1 or random values between -1 and 1, floats. And then there we go. We now have a signal filled with random junk. So that's simple ways of filling a signal. But we're going to use a method. Just start again here with zeros, 513, and wave fill. Is that right? No, not, we're going to use sig.wavefill. And do we have to actually do sig equals? No, I don't think we do. I think it actually overwrites the data in place. So sig.wavefill, this is a method for instances of signal. And we start with a function, which is passed 3 arguments, which I'm going to call x, y, and I. And what we're going to do, well, x is the value along the x-axis, and we can determine the left to right range. Y is the value stored in the wavetable, and I is the sample index. So what I'm going to do is just post these. And then return y, because what this function returns is going to be what's then stored or overwritten at each value in the signal. And so I'm just going to return y because that's what already exists, and so this means we actually don't modify these values. We're just putting what's already there in place. And then a start and an end. So we're going to do 0 to 1 because those are the default values. And if we then run this code, we can see that we get the signal is returned to us still with zeros, just like we left it. And then in the post window, we see all these post ln calls. So our range, we're saying that the left side of the signal, the beginning, corresponds with a value of 0, and all the way on the right is a value of 1. And these are the values that get passed in as x as the first argument. So they start at 0, and then they go up by 1/512th each time. Y, those are the values that are in the signal. So currently those are 0. And then finally, I is the sample index. So it starts at 0, and it goes all the way up to 512 because there are 513 values, but we start at index 0. Is this making sense so far, everybody? I know this is not glorious or exciting as far as wavetable synthesis goes, but we will get there. I'm just trying to explain how this wavefill function works. So instead of returning y, let's put a comment here and just say post values, no change to signal. So now let's fill signal with linear ramp from -1 to 1. Cool. Thanks to Derf. Okay, so now that we've seen those values, we don't really need to post them. So one way to fill this signal with a linear ramp, here's one way you can do it. We're going to return the value I mapped from its original linear range of 0 to 512 onto -1 to 1. So before we do this, let's just take a look at our signal. And it's all zeros. So there's just a black line along the horizontal axis. But then if we do this, it returns our signal to us, and just in the post window alone, we can see now the values in the signal start at -1, and they increase by a linear amount each time. And if we then plot this, voila, we have a linear ramp. We could, one advantage of using the index is that this value doesn't change. So no matter what is in the signal, if we're generating new values using I, it's gonna it doesn't really matter what the existing values are because the index is always the same. So we could do something like squared. So I guess take a second and try to imagine what this is going to look like. We're mapping to we're taking the index, generating a linear ramp from -1 to 1, and then we're going to square those values. So positive or negative, anything squared becomes non-negative, so 0 or positive. So if we do this and then plot it, we have a lovely parabola, which starts at a value of 1 and in the middle dips down to 0 and then back up to 1. And yeah, so we do this with a function, and the function can contain any sort of valid code. So let's go back to our linear ramp, and in the context of wave shaping, this signal, it's going to get turned into a wavetable, but this is the essential shape. This is the kind of shape you'd see in a textbook if you look up a transfer function for wavetable synthesis. And a transfer function, receives some input signal, and that signal is going to be a bipolar signal, something you'd play through your speakers, ranging from -1 to 1. And this function shows you the input-output relationship. So, and this is what you might call the identity transfer function. A value of -1 that comes in along the x-axis produces a value of -1. A value of, I know this isn't technically 0 because we're looking at the number of samples here, but just imagine we have -1 here and +1 here and 0 in the middle. So a value of 0 from the input wave, or the input signal, the input waveform would produce a value of 0 coming out, and a value of 1 would produce a value of 1. So whatever comes in goes right back out. So if you use a sine wave as an input to a wave shaping function, you get a sine wave out if this is your transfer function. A sawtooth wave comes out. A sound file, the sound file comes out. It has no effect whatsoever. So we might as well demonstrate this. So let's turn this into a wavetable. And we do this with sig.as wavetable no wrap. I regrettably did not take the time to learn precisely what is meant by no wrap. There's a as wavetable and there's as wavetable no wrap. What I do know is that if you're going to be using the shaper unit generator, we do need to use no wrap. So if we do this and then check the size, I believe wavetable is a collection as well. We can see that it is now 1024. Our signal was 513, right? And when we take a signal whose size is power of 2 plus 1 and turn it into a wavetable using the no wrap method, we get a wavetable that is a size of the power of 2, and that's what we want for shaper. At least that's what I've seen. I would sort of expect something here. Maybe there's, well, we can see we're allocating a 512 buffer there. I think there was something I saw in the help file. Yeah, or for an arbitrary transfer function, create the data at half the buffer size plus 1. So that's what I gathered from the help file. So I think we're doing it correctly here. That's not to say that it won't work correctly or incorrectly if your wavetable doesn't have a power of 2 number of samples in it. I don't know. Maybe it's worth messing around with, but we're going to do it this way because that's what we're doing. All right, so let's take a look at, we're going to now plot this wavetable. And yeah, so what are we looking at here? We have these two graphs which definitely look similar. This one behaves normally when we shrink or grow the window. This one does some weird stuff, which looks pretty cool. And what's happening here is that this is actually visual aliasing. The this plot is of a wavetable. Now this is what it sort of normally looks. This is as accurate as we can get. It's trying to represent 1024 samples or pixels, and now we actually have that many, but now this is less than. So it's representing multiple samples per pixel, and so we get this trippy behavior here. I'll tell you what, we're gonna just plot a few of these because I do want to show what is going on with wavetable format, if I can. So let's do sig at from 0 to 20. Is that going to give us? Yeah, we'll plot that. And we'll do the same thing with the wavetable format. So there's that, and there's that. So we're only looking at the first 20 samples in each of these. And the way wavetable format works is it interleaves the values of the signal itself with values corresponding to the difference of consecutive samples. So here in the wavetable, we have our first sample value, -1. And then in our signal, our next value is simply our next value. But in the wavetable format, we skip one value, and then that value gets stored here. And the in-between value is the difference between this and this. And I think it's slightly positive. And because this is a linear function, the difference between successive values is always the same. It's always this very, very small value close to 0. So we have -1, the difference between that and the next sample, and then the next sample, the difference between samples with index 1 and 2, etc., etc. So, and the reason this wavetable format exists, I believe, is for efficiency. I think it's just the server has to do less work in calculating. Sometimes it's, in a lot of cases, I guess, this, some audio processors would actually have to calculate the difference in order to do certain things with the data. But here they're actually stored in the collection, the wavetable, as they're actually stored there. And accessing values in a table is super easy and fast for computers to do. So if we were to do, let's see, dot cubed, and now we'll plot this and plot that. That's not right. We forgot to turn it into a wavetable. So here's this, and here's this. So again, they look similar, but the wavetable has the interleaved values. So yeah, I guess we could sort of briefly look at a few of those. Yeah, so again, we've got the sample values themselves at index 0, 2, 4, 6, 8, and then the differences at indices 1, 3, 5, 7, 9, and right. So that's wavetable format. That's why it looks sort of funky. How's everybody doing so far? Have I confused anyone? Bored anyone to death? Okay, so let's go back to our identity transfer function and turn it into a wavetable. And just gonna check to make sure it works here. Yeah, that's what it looks like. Okay. Cool. Well, I think it's interesting too, for what it's worth. There's lots of audio software out there that'll let you make cool sound really fast, and that's really valuable. But I sometimes like to pick things apart and really understand how they work. Okay. Let's do a signal and an index. Our index is going to be, we'll start with a sine wave at 500 hertz. Full amplitude for wave shaping purposes. I will turn it down at the end because full amplitude hurts me. Full amplitude is not for the faint of heart. And then we're going to use shaper. And shaper is quite a simple unit generator. It simply takes a buff num. Oh, so we actually do need a buffer. We can't just plug a wavetable right in there. So what we're going to do is make a buffer and use, I think you can use load collection or send collection. The difference has to do with like whether you're on the local server. Like one of them only works on the local server. I should check this before I just mix stuff up here. Yeah, well, load collection will reload a large collection into a buffer on the server. And what's the difference between that and send collection? Right. For this reason, load collection will only work with a server on your local machine. For a remote server, use send collection. So I'm working locally here, so I'm going to use load collection. Okay. We're going to local server and our wavetable. And that's all you need. So we're creating a new buffer and loading into it our wavetable collection. So now if we plot this buffer, it should look exactly the same as our wavetable plot, and it does. Except now this is actually a buffer. That's good. So for the shaper, unit generator needs two things. The buff num of the buffer filled with data in wavetable format, and then the input signal to the shaper, which is going to be used as an index into the wavetable. So this would be b.buffnum, tilde b.buffnum, and then our index. And I'm going to do sig equals sig times 0.3 exclam 2 to make it a little bit quieter and make it stereo. And then we're going to play. And what we should hear is a sine wave at 500 hertz because our buffer contains the identity transfer function. And we do. We hear exactly what we would expect. And let's get our good friend, the scope. Not the scop, the scope. Thank you. And now we got to find a good place to put this. I'm going to shrink that down. I think we have room to spare, hopefully. I like a big scope. But we got this chat window here. I will shrink. You know, we're fine. We're fine. This is all good. So if we play it now, is that too loud? It seems a little bit loud for me. I'm gonna make it a little bit quieter. And I like to adjust the scope so that the waveform looks like it's sort of standing still. See if I can do that. What if we do this? No, other way. Ah. Yeah, so this scope has a refresh rate, and depending on the frequency of the waveform being displayed there, those can sort of line up. And again, this is an example of visual aliasing. So it just happens to be taking a snapshot at a multiple of this waveform's period. So it just allows us to, really inspect the waveform nicely. So no matter what we put in, let's do a Sawtooth Wave. Right. Or maybe a pulse wave. Or a triangle wave. Wave shaping is happening, but we're using the identity function, the identity transfer function. So let's change that, because the identity transfer function is not useful from a synthesis point of view. Okay, so what we need is an idea for an interesting transfer function. And let's think about this. Any suggestions? Go ahead and shout them out. Okay, so here's something. Let's just invert that. So now we have this. So a value of -1 returns +1. And the opposite is true. A value of +1 returns -1, right? So, and 0 is 0. So what this effectively does, and maybe you guys can sort of figure this out, hey, Twit My Itch, how's it going? What I'm gonna do here is we're gonna change the scope so that we can see the input to the shaper unit generator and the output. So we're gonna do s.options.num output bus channels equals 4 and reboot the server. And oh no. Okay, hang on. That was, I heard something weird in my, okay, let me quit the server real quick. And I started hearing my microphone in my left ear. That's not what I want. Oh, this is, probably make it 6. No, same problem. Oh. Okay, do not want feedback. Is that producing strange sounds for anyone watching? I really want to be able to show this, but I think this is a consequence of the aggregate audio device that I made in my MIDI setup here. Yeah, it's because I have. All right, so what if I just go back to built-in output, like use this for sound output. Okay, so we're gonna fix this. We're gonna spend a little bit of time trying to fix this, and then we will see if we still have the problem. So now if I boot this, let me just, do we have sound? We lost our, okay, let's make a simple noise. Okay, please work, please work. No. Why would this be happening? So Output. What is SuperCollider's? Maybe I can just change SuperCollider's input device so that my voice doesn't come into SuperCollider. I think that'll work. Because what is currently being used for input? Sorry for the technical problems here. Is it Soundflower? No, it's the Sapphire. Okay, but that's fine. What if I just change that to be like Soundflower 64 channel or something that I don't use? Yeah, I have no idea why there was that reverb. I'm kind of assuming that was feedback. Devices. We're gonna use this because I think that's not being used. So now let's see if we change the number of channels to 4 and then reboot. Do we still hear my voice? I think that's good. Let's see if we have... Yes, okay, I think we're in business. I see signal in OBS. So you should be hearing pink noise. Let me know if you are. And you should still be hearing my voice. But now if we bring up the scope, we should see 4. Yes, that's what I wanted. Okay. So now we're looking at the 4 hardware output buses, even though we're only using 2. I guess we still need to sort of test this. So if we do out.ar0, pink noise, this should be left channel. This should be right channel. Okay. I don't think... what should happen here is that we should see signal, but not hear anything. Yes. Okay. All right. So now, back to business here. Right. We made our inverted signal, right? Which our transfer function now looks like this. It's been flipped vertically. And our wavetable looks like this, as it should. And then we read that into a buffer. Here's our buffer plot, same as the wavetable. And now if we use, let's start with a sine wave again, as our index, we're going to out.ar this to 2. And I guess we'll multiply it by 0.1 exclam2. And we're also going to, this last one, I guess we could be explicit about this. I'll put that to, we don't need to say sig equals anymore. So if we do something like this, see, I want to hear the shaper output. So that's why that's going to show up on 1 and 2. And then we're also outputting the input to the wave shaping table. That's going to show up here and here. So let's try this. See if we can find that sweet spot again. Just got to get close. Okay. So, as you can see, what's happening here, make this just a bit quieter so I can hear myself talk. I don't know how, let me know how the sine wave to voice volume is, if one is too quiet or too loud. But here on the bottom we have our input signal, and so it's a sine wave, right? And our transfer function, I'm going to plot the signal because that's easier to read. What it does is it inverts the waveform, which doesn't do anything particularly interesting sonically, but it does give us a little more insight into how... More voice. Okay. Can turn that down a little bit. Okay. Right. So where's my plot? So what happens is all the positive regions become negative regions, and negative regions become positive regions. So that's what this particular transfer function does. We can do something more interesting, though. And just to show you, if we take another type of wave here, let's so yeah, now again, same thing. We invert the positive and negative regions become inverted, so that's all there is to it. Okay. Right then. Okay, so let's make something crazier here. Well, any suggestions? Any suggestions on a wackier wavetable function? I sort of want to do something instructive, not something too chaotic. We could go back to our cubed, maybe cube it twice. So this now looks like this, right? Oh, and it's inverted. Okay, but that's fine. It doesn't really matter. Yeah, okay. So I'm gonna be upfront with everyone here. I do not know what a Chebyshev polynomial is. I do know that there are methods, like Chebby fill, which allow you to fill a buffer or a wavetable with a Chebyshev polynomial. So we get some interesting shapes. I just can't speak about them mathematically. And I didn't actually look into the methods. I didn't sort of practice with those. So maybe we can mess around with those. That's a good suggestion. So if we look up Chebby fill, so apparently you can just create a wavetable just like that. Fill a wavetable of the given size with a sum of Chebyshev polynomials at the given amplitudes for use in... So this is basically exactly what we need. So let's try that. Why not? Let's do W equals wavetable dot Chebby fill 1024, and then amplitudes, an array of amplitudes for each Chebyshev polynomial beginning with order 1, whatever that means. I have no fewer than 3 math PhDs in my immediate family, so I would not have a problem getting answers to questions about Chebyshev polynomials, but I just don't have them right now. So I'm just I'm going to be just plugging in numbers. So let's do... Well, that's a good place to start, definitely. I'll read that. I'm not going to read it now because I don't think anyone wants to watch me reading Wikipedia on stream. But that'll be my homework. I'm actually going to write that down, because it's probably a good thing to learn about. So what if we do 1 over the array 1, 2, 3, 4, 5, scramble that. So this will give us the array of those fractional values randomized. And I think that's all we'll do. So there we go. Size. Oh, it doubled it. Or interesting. What if we do 513? Okay, that's what we want, I think. That's consistent with what we've been doing before. And now we have this shape. This is our wavetable. And I think there's an extra step added into the generating process for Chebyshev polynomials that ensures that when you put in a value of 0, you get out a value of 0, and that avoids DC offset in the output signal. And that's something that I'll demonstrate as well. So, okay, fine. We got our Chebyshev polynomial wavetable. And so now let's see if I could use a sine wave, but I'm actually going to use a low frequency sawtooth wave because it's a linear ramp from -1 to 1, which makes it the ideal waveform for showing what's actually going on in wave shaping, because it just goes from -1 to 1 linearly, and so it reads through the values in the wavetable sequentially and repeatedly. Yes, I can definitely explain that. I can't explain the implementation of leak DC or what's actually going on under the hood, but what it does is it simply centers the waveform vertically on 0. You know what? I can do that right now, just because you asked, and I'm happy to oblige. Let's take a look at a sine wave, regular old sine wave. And since we have our scope, I guess we'll keep the frequency the same, and we'll make it stereo just because it's a little bit nicer to listen to something in each ear. Right? So this is a sine wave with no DC offset. DC offset is it's a vertical shift in the waveform, either up or down. And we can artificially introduce that, well, I guess actually introduce that by providing a value for the add argument. And this adds a value to the output of the waveform. So if we do, 0.3, I think that was a lot. Yeah, okay. So we'll just do this incrementally. 0, 0.05, and 0.1. And yeah, eventually we see the waveform start to shift, and we can go the other way as well. And eventually it gets to the point, yeah, DC bias is another word for DC offset, another way of talking about it. Wikipedia is a great place for information. There's no two ways about it. So if you have a waveform that's being sent, that's being, D to A converted and sent to speakers or headphones, generally it's bad to have a DC offset in that signal. A nice normal signal like this will push your, that's okay, loudspeakers out and in, equally, and this is what loudspeakers like to do. They like to go out and in and out and in. And if there's DC offset, then in this case, they're always pushing, and it just means that the cone is sort of not centered around its equilibrium. And that's generally something you want to avoid. I think it's just bad for speakers, is the bottom line. So when we're doing wave shaping, if we have, imagine we have our transfer function is, mostly up in the positive range. It's sort of squiggling around up here, and a value of 0 on our input signal is going to produce some positive value. And so, this is going to give us, like if we have silence, like if we send silence through our wave shaping function, it's actually going to come out with a DC offset because the value returned at 0 on our wavetable is non-zero. So that's why the Chebyshev fill function has this special, thing built into it to ensure that a 0 value always produces 0, because that avoids DC offset. But what you can do if you just want to be sloppy and have whatever kind of crazy wavetable you want is you can use the leak DC unit generator, which is a filter. It's basically a filter. That's all there is to it. I mean, if we think about filters in their most general definition, it's something which takes an input signal and produces an output signal, which may or may not be different. But it somehow filters the waveform to remove DC offset. I don't know too much more about it other than that. So here's our DC offset signal, and if we say our sig equals our bogus DC offset signal, and say sig equals leak dc.ar, and just put that signal in there, it fixes it. It's like magic. Right, so if this was offset by some other small amount, a little bit less, so there's still DC offset there. It's not quite as severe, but again, leak DC, it just gives you a nice healthy looking signal. It's one of those unit generators that I think a lot of people might actually just use instinctively at the end of synth defs because it doesn't hurt, I don't think. I've never heard of anyone experiencing leak DC exploding or giving some crazy values. But anyway, yeah, it's sort of like putting a limiter at the end of a signal chain or something. It's just, except in this case, it's a filter to avoid DC offset. Not a problem. Happy to do it. Okay, so we have our, this is, I think we re-scrambled our values, but we now have this function here. And we'll keep this open, I guess. Sort of like this. Something that looks sort of nice. We can try to make it look sensible. All right, looks kind of cool. Okay, so then if we send our Sawtooth Wave through this, we have to actually turn this into a thing. So now, right now we've got it in a buffer. Very good. So now, if we use a low frequency Sawtooth Wave, again, just a linear ramp, it's going to index through this table at the frequency that we give it. So 507 times per second. So without further ado, and I know this sounds horrible, like it's not a pleasant sound, but bear with me here. See if I can. Let's try some other values here. If that's really annoyingly loud and piercing, I can turn it down. In fact, I might turn it down just a little bit. I suppose we don't really need to listen to it to explain how it works. Come on, work with me here. Okay. Twitmich, not totally sure what you're asking. To deal with higher signals, could volume equals -10 help? Yeah, that could work. I usually don't do it that way. I assume that just sort of adjusts this thing here, which is not working. Let's try your way. Yeah, is it decibels or is it amplitude? Because I would be a little bit nervous about just putting a -10 because I can also just turn it down in OBS. I mean that's probably the easiest thing to do. Okay, I'll play around with that off stream just so I don't blow anyone's ears up or something. I trust you. I do. I've just never done that before. So, but okay. So anyway, what we've got here, and I am going to just turn this down just so not too loud because it's kind of annoying me too. We've got our input signal, which is this Sawtooth Wave. Right. Can we fine tune this even more? And it is reading through this Chebyshev polynomial. You can see that shape there from -1 to 1 is exactly like what we see here. Right. And if we were to use now, for example, a sine wave, now we have something sort of totally different. Or maybe let's do an intermediary step and do a triangle wave. So a triangle wave is a linear ramp up and then back down. So this is going to read through the polynomial this way and then reverse it every cycle. So we should be able to see that if we do that. Right, here's our polynomial this way and then coming back the other way. And that's one cycle of our input triangle wave. Right? And a sine wave is like a triangle wave in that it goes up and down, but it's curvy. So it doesn't read through the wavetable linearly, it reads through it sinusoidally. Which gives us sort of a smoother wave shape, which means the an analysis of this wave-shaped waveform is going to have fewer higher harmonics. So yeah, that's that sounds kind of cool. Yeah, so that's an example of a Chebyshev polynomial wavetable. So let's see if we can just take a look at this cubed version here, right? Which again is this guy here. And if we turn it into a wavetable and load it into a buffer, here it is. And let's again use a low frequency Sawtooth Wave. Right, and you can see there's our shape right there. What I could do is just take a picture of that, and then that way we can look at it and not have to listen to it. Yeah, so here's our ramp, -1 to 1, and it is simply reading through this wavetable and gives us an entirely new wave. And a sine wave would give us this. But okay, things get more interesting here. If we change the amplitude of our index signal, let me answer this question. So once you have your own wave shape, could you create a class for it, then use that as an index? I mean, I don't understand how that's too much easier than just making a bunch of wavetables at the beginning. I mean, there already is a class for wavetables called wavetable. And I mean, you could make like a function or like a method that generates some sort of custom wavetable, I guess. You know, like you could put this in a function and save it. I want to eventually, you know, on this stream, get to making some really weird wavetables. Maybe I can show some of the wavetables that I made in my sketches file. I think I'll do that eventually. So what was I gonna do? Okay. Okay. Here's what I want to do. You don't always have to start with a signal. You can start with an env, and that's what I'll do here. We are gonna make 11 random values with, this is similar to the one that we saw at the beginning of the stream briefly. 10, because we have, you know, one fewer, the number of segments is one fewer than the number of points. And then -5 2, 5, and 10. And let's plot this. This is going to give us, whoa, that's not right. What is that? What are we even looking at here? Hold on. Oh, okay. I see what I did. That was interesting. I have an array, or a collection, and then this is also an array. So I have an array containing 3 arrays, but that's not what env needs. It just needs 3 arrays, not contained in a parent array. Yeah, this is, sorry about that. Okay, so here we go. Here's a funky looking envelope. It's got this really long duration at the beginning, and then a little dip, and you know the rest. So, but that's an env, right? That is, oh no, it's actually a plotter. So let's not plot that. Oh, we're gonna lose it. We're gonna lose our beautiful envelope. That's okay. Say goodbye. It's gone. The problem is I set sig equal to an env.new.plot, which returns an instance of plotter. So it's not actually an env. But now, if we just plot it without storing the result, it is in fact an env. So, right. But we don't want it to be an env. We want it to be a signal so that we can convert it into a wavetable and load it into a buffer. So we can use sig dot as signal. What could be easier? And we just need to know the length, and it's going to be power of 2 plus 1. And I think we need to do this. Now it's a signal, which means we can do this, and we might as well plot that. Now we've got a wavetable. And you can see there's a lot of positive values here, and somewhere in the middle is not returning 0, so we are going to have DC offset, and we're going to have to undo that. So then we load it into a buffer, and now we will play it with a Sawtooth Wave. Right? So let's see. Here we go. Let's look at our this. And as you can see, as we go from -1 to +1, we are, there's our notch, right? And then we have our first notch at the very beginning. And then the second little notch here is right here. And then we have our big tooth here, whatever that is. So yeah. But okay, so that's, again, we've used an envelope and then to generate, because envelopes are cool because maybe you're more familiar with generation methods like env.new, env.perk, env.try, and you can also just use env.new to just make whatever you want, some very highly specialized custom shape, and you can turn it into a signal, wavetable, and load it into a buffer. So where you'd put leak DC is here. It happens, so you have our index, and then we apply the wave shaping, and if you have a funky sort of wavetable, you get DC offset, and so you just correct that immediately by overwriting the result. So the sig, the DC offset sig is equal to a leak DC version of itself. So now you can see that our wavetable, let's see if we can bring this up again, sig.plot, right? Same shape, but it is nicely centered, right? So yeah, you just want to, yeah, after the wave shaping takes place, but before we actually send it out. I would just do it immediately after the shaping. Okay, so more interesting stuff here. What we've been doing is cool. I mean, I hope that the process of indexing into a wavetable now makes sense, but we do just get this sort of static sound, which is maybe not the most pleasant thing in the world, right? You know, you get all sorts of interesting stuff. Let's do a pulse wave. Yeah, so the pulse wave is sort of jiggly, and so we get this jiggly stuff. Okay, I'm getting carried away here. Let's look what happens if we multiply our index by mouse X going from 0 to 1. And we'll poll this so we can see. So let's go all the way down to, let's do it almost all the way down to 0. So this is an amplitude scaling process. We're simply multiplying our index by a value between 0 and 1, depending on where the mouse position is. So on outputs 2 and 3, you will see, as I move the mouse left and right, that wavetable get taller and shorter. This Sawtooth Wave is going to get, going to have its amplitude modulated. And when it's full amplitude, -1 to 1, it's going to read through the entire wavetable, because here's -1, here's +1. But if we shrink the amplitude, if we reduce the amplitude of the index, say to positive and minus 0.1, it's only going to read through the wavetable here, right? Just the middle part. So we're just going to get this little bit of shape in the middle. So it's sort of an interesting thing to watch here. So let's see if I've done this correctly. Can I make this bigger and without ruining anything? Yeah, I'm gonna make this a little louder just so we can actually, because I'm zoomed in all the way vertically here. So I'm gonna increase this volume a little bit. And mouse X, it's okay. It's using my my main display, my laptop screen, which is not on stream. So that's why my HD TV is actually a fewer number of pixels. So that's why it's only going to point. How far is it going here? Yeah, 0.82, and there. So I'm gonna put the mouse on my main screen, so you won't see it, but you'll still see the waves on the. So yeah, so there is our full wavetable, and as I move the mouse to the left, we're ignoring the extremes of the wavetable, and so we get a different wave shape. Right? You can actually see the wavetable sort of being exposed. There it is, and now we hide it away. So we can do something like instead of mouse X, running out of space here, we can do a sine wave. Sinos.kr, 0.5 hertz, range 0.2 to 1. Something I will sometimes do just to make things more interesting. Oh yeah. Yeah, you could do that. Let's do that. Sometimes I'll do is I'll just change the frequency. This is not related to that question, but just change the frequency of the index to be, a stereo. So we have a slight binaural beating thing going on. If you have headphones, it just sounds more interesting. Oh no, I did it wrong. I've done this before. If it's stereo, we don't need these exclam2s. That screws things up. So this should be, yeah, that's what I wanted. And maybe a sine wave would be a little bit more mellow. Well, not really mellow. And it's, let's see if I can take a picture of that real quick. Yeah, when the amplitude of the sine wave is, well, I mean, it could happen at any time, I guess, but we've got this wavetable, and depending on where we read to and from, there could be a discontinuity, and it sort of looks like there is a discontinuity, like here and here, maybe. And and a discontinuity in the resulting wave-shaped signal gives you this piercing high harmonic sound. If we bring our mouse back here, you can see that at some amplitude levels, what did I do? Semicolon. And let's do our low frequency sawtooth wave here. So here, right here, the amplitude of the index, the sawtooth wave, happens to be very specifically set so that the beginning and end of the section of the wavetable that's being read are nearly the same value. And so we get sort of a smooth, continuous waveform. But then if we shift it a little bit, we then introduce a discontinuity. You can see at the very top waveform on the scope. Right? Now they're almost the same, so we get a pure sound with fewer high harmonics, or less prominent high harmonics. And then we have this discontinuity. And right. And now we have there we go, the ends meet. Now they don't. Now they don't. Yeah. So I've never actually tried this, but if instead of an oscillator, we could use an envelope. It's got to be audio rate. Let's not delete stuff, but instead comment stuff out. Let's be responsible programmers. Index equals env gen.kr env.new. No, not kr. I just said it has to be ar. So what kind of envelope were you imagining? The derf. If you had anything in mind. The thing is now, though, it's going to let's use our new.ar2. Okay, I'll make something up then. Let's start with, I'll start at -1. We'll go to +1, down to -0.5, and stay there, and then up to +0.5. I could type correctly. And then back to -1 and +1. And let's do random values between 0.1 and 0.5. And we have, how big is this? 8. So we need 7 of these. And we'll just make this linear. Let's plot this. Here's our index. This is going to be fed into our wave shaping function. And the thing to remember here now is that this is not an oscillator anymore. It's an envelope, so it's got a finite duration. So it's going to do this once. Let's try it. Oh, okay, that wasn't very interesting. Yeah. Maybe I misunderstood. Maybe you were suggesting an envelope to control the amplitude of the oscillator index that's fed to the wavetable. Because I think we really do need some sort of audio rate oscillator that's, you know, cycling through something at least 20 times a second. So I think, yeah, this approach may not be particularly interesting. I mean, we could make the we could loop the envelope and change the duration values, so you'd have some weird custom oscillator, and then we could set the oscillator to loop, I think the release node 0, 1, 2, 3, 4, 5, 5, 6, and 1. 1 would be just gonna, yeah, so now it's looping. So if we make these values smaller, yeah, it's doing something. Definitely doing something. I think we want to make this stereo. Yeah. So there you go. That's sort of what you were. Use the envelope to read certain sections of the waveform, and at different times, like really fast, to get more variety. Yeah, what I would do in that case is just use a noise generator. You know, like LF noise 1 or LF noise 0. Well, not 0, because that's non-interpolated, so it's just going to jump to various samples, I think. But LF noise 1 might be kind of cool. And then you could also use like fold or wrap or something weird on the noise generator. Yeah, this is like, now we've turned an envelope into an oscillator. Which is kind of cool. I mean, it's working, I think. Like if we take a look at what's going on here, where is my, we still have that plot of our, yeah, I think this is still our wavetable here. And see if we can just try to get a sense of what's going on here. Yeah, so here it's starting at the bottom, right? This little jagged part here, that's this at the beginning, because the index is at its lowest point, at -1. And so then it starts reading through, but then stops halfway through, and so we get this flat part here. And yeah, so it is working, but let's go back to what you were suggesting. Yeah, patterns make everything more interesting because instead of just playing a single synth, you are just generating thousands of synths in sequence. Yeah, so this is, I mean, obviously, I would definitely eventually put this kind of stuff into patterns, and I have done so over here. But let's try a noise generator. Let's see how that goes. LF noise 1.AR. We'll set its frequency to like 40 for now. I mean, I think this is going to produce noise because there's no frequency. Oh, there's a frequency at which random values are generated, but this may not be as interesting as you think it's going to be. I'm sort of guessing it's going to be pink noisy-ish, maybe even white noisy. I don't know. Okay, but we'll make sure to set its range. Just, I forget. Range -1 to 1. But that's the default range. I don't need to do that. So should be, yeah, very similar to what we just did. It's the frequency is kind of low, so if we ramp this up, you know, if noise is your thing, here's a new flavor. Yeah, that's that's a pretty good approach, I would say. It could work. I just find it sort of easier to work with just oscillators because they, I mean, if it's, it depends. I mean, if you want to make pitch or you want to make noise, if you want to make pitch, you should use an oscillator, whether it's an envelope that loops or a periodic generator or something. Yeah. So I think noise in, noise out is the rule here. If you put random values in, you're going to get random values out, even if you're transfer function is something regular. So here's some other interesting, yeah, let's take a look at what I've done here. I'm going to copy this into a new, copy this in here. Oops. Okay, yeah, sure. So transfer functions that require math. Let's make another. Let's start with another empty signal. Right, and here's our. So let's. This was our random signal from envelope. So I'll be honest. I don't. You know, I'm no expert on trigonometric identities and functions. I know enough about trigonometric functions, you know, sine, cosine, whatever. So I mean, you can make a transfer function however you like. We've only really been using the index here. So let's do something else. Let's set our range to be 0 to 2 pi. That's a good place to start if we're going to do trigonometric stuff. Right? One cycle, like a full circle here, and forget about this. Then we'll trigonometric stuff. So if we were to do something like sine of x, that's going to take the sine of these values, which are, you know, start at 0, and there are 513 values, and they go to 2 pi. So if we now plot sig, surprise, surprise, we have a sine wave. But this is not going to play a sine wave. This is our transfer function. So interesting stuff will happen. I don't know. Let's make that a wavetable. And here's our wavetable format transfer function, sine wave. And then we will load it into a buffer. And now, if we feed a sawtooth wave, a low frequency, a pure linear ramp into this shaper, what we get out is going to be a sine wave. What did I do wrong? Did I get some error somewhere? Let's just do this again, because that was not a sine wave. So that's that, right? And you can see that's working. And W equals sig dot as wavetable no wrap, right? And okay, and there's our buffer. And oh, maybe not. Is this related to the 2 pi thing that I did? Oh, it's okay. I know why. It's because I don't have the mouse all the way on the right side of the screen. So we're only getting part of the sine wave. There we go. That's what I wanted. Right. And let's shrink this down a little bit and maybe. Yeah. Right. So with a full amplitude Sawtooth Wave, we read through the table completely, which produces a sine wave. If we read through it not quite all the way, then we only get a part of the sine wave, a smaller and smaller part. Okay. And just for fun, what happens if we use a sine wave to index into a sinusoidal wavetable? Ooh. Yeah. Right, because it's going, the sine wave is reading through the table sinusoidally forward and back. So we get this particular shape. That's cool. And then you can do stuff like do it again, right? So use the signal as an index into the buffer again. Is this going to work? Oh, yeah. So then we can do... Your internet bugged out. Has it stopped bugging out? So check this out. We can do like 2.do that thing. So now we're wave shaping once, twice, 3 times. Yeah. So that's just another flavor you can do. You know, just wave shaping in series. Okay, but the question was just transfer functions that require trigonometric math. So what I usually do is how about feeding it back into itself as an index? That's what I just did, isn't it? Did I not understand what I was doing? Yeah, so we have an index. It's a sine wave, and it's used as an index into a wave shaping table. Yeah, and then that's the result, sig. And then we use sig as an index into that wave table again and again and again, as many times as you want. So if we did something like 5, I think eventually you'll get sort of crazy aliasing artifacts. Yeah. Yeah, okay. That's enough. So I think that is exactly what I'm doing. Space-time. Okay. So when I am making wavetables that I think will sound interesting, I usually just experiment. Like, I don't know what I'm doing. I mean, let's do sine of x squared plus cosine of x square root. I don't know. There we go. It looks like this. So I don't know exactly what you meant. Can you go over transfer functions that require math? I mean, if you have a shape in mind that is sinusoidal or exponential or something, it's good to be able to know how to turn that into a mathematical expression. I am sometimes good at that and sometimes not. You know, it would help if maybe if someone had a suggestion on like, oh, what about this kind of shape or something. There was one that I made. I think I already copied it in here. Right. So this one we've seen already. Here's my first wavetable that I put into my sketches file. It's just this random envelope thing, and the syntax is a little bit different. I just do things in an order here. I have my wavetable equals dictionary.new, and then we add a buffer.load collection. And that buffer is being loaded onto the localhost server, and then I evaluate a function which returns a signal. And so here's, if we start, let's just maybe unpack this a little bit. So the first thing we do is we make our signal. All right, sig equals nf.new, and it looks like this. We need a var sig. Yeah, okay. That's not it, it's this one. Right? Windows all over the place. Okay. So we turn that into a signal, making sure to give it power of 2 plus 1, right? And right, so now it's a signal. And then what I've done is sig equals sig.normalize, because this may, we're actually almost certainly not going to get a value of -1 or 1, but I do want the wavetable to occupy the full digital amplitude range of -1 to +1. So we normalize it and then return, so this is our sig. So we return it, and then I put this in a function. And so this returns a signal, right? X equals this stuff. It's the evaluation of this function, which returns a signal. So X is now a signal. Right, and here it is. And then we turn that into a wavetable. And then the last thing we do is we have B equals buffer.load collection S, and then this function, which is then evaluated and turned into a wavetable. So this is how you can do it all in one step, like this. And then, so if we do b.plot, sure enough, we have a buffer which contains our segmented random envelope as a wavetable in wavetable format. So that's the syntax that I've been using. Okay, so let me unpack some of the other wavetables that I've done. So yeah, I don't know if this is instructive to show all this gobbledygook, but so this one, in my function that generates a signal, I have sig and mod. And what I wanted here was something which was sort of sinusoidal. So a few low harmonics, but then I wanted to randomly have these bursts of stuff. So if I, let's do this. Let's just run this. And then if we take a look at wavetable at symbol1.plot, it looks like this. So as you can see, it's sort of sinusoidal, but it's got some higher harmonics. But then every now and then I've put this bursty noise thing in there. And I'm using that as my wavetable. So the way it works is I'm using the signal.sine fill. So, and then it's that should be 513, shouldn't it? Right? I think it should. I'm so irresponsible. Okay, but anyway, yeah, sine fill takes a size and then an array of amplitudes and an array of phases. So I have 1, right? So that the fundamental has full amplitude, and then we concatenate that with an array of 15 random values, which are all kind of small. So harmonics 2 through 16 are all present, but they all have low amplitudes. And the fundamental is in phase, it has initial phase offset of 0, and all of the other harmonics 2 through 16 have a random initial phase, right? And then I have, I'm creating an array. Oh yeah, I'll keep the GitHub with this. I mean, I'm starting to feel bad because let's see. Okay, let's clean up a little bit here because it's kind of a mess. I mean, I'll post all this stuff. I'll clean it up a little bit, but all of the stuff you see on stream will be on GitHub. It might be a little messy, but I'll add some comments, and yeah, don't you worry, it'll be great. Where was I? Okay, so yeah, I fill an array. It's gonna have 4 to 7 items in it, and each of those items is gonna be an array of 1s. So that looks like this. It's an array. So here's an array of 1s. Here's an array of ones. And then I add more things to the array so that it has a, a total size of 513. And the rest of those things are 0. And then I mix everything up so that the clumps of ones stay together, but it's like, a whole bunch of zeros, a clump of ones, a bunch more zeros, a clump of ones, more zeros. And so it's all randomized. And then I use my wave fill method, which you've seen already. And basically, on each time it needs to say, okay, what value goes into this signal at this index? I check the mod, which is the array of zeros and ones. I can actually look at the array. So now here's the array. It's got the ones and it's got a bunch of zeros after it. And then if we scramble it and use the flat method, it becomes a one-dimensional array with zeros and then a group of ones that are all clumped together. And if we were to keep going, we'd see another clump of ones, anywhere between 4 and 7 clumps of ones. And as we generate the array, as we fill the signal, we check the corresponding index of this 0 and 1 array. And if it's 1, then we take the old value and add some random value to it. So we turn it into noise, basically, to just add some random value. And we make sure to fold. I could have used clip or wrap here just to make sure it stays within -1 to 1. But if mod at I is 0, don't do anything. Just leave it the way it is. So we have our harmonics here, our simple sinusoidal thing, and then we go through that signal and scramble the values that correspond to these sections of ones. Maybe I can unpack that a little bit. Right, so we have our sig equals signal.sine fill 513. If we just do 1, 0, this means we have just the fundamental with an initial phase of 0, which looks whoops, semicolon, and it's got to be an array, I guess. Yeah, boom. And we can do the array 1. Let's just do 1 0 1 0 1 0 1 0 1, and that's 9 things. Right? So we'll just have all their phases be in phase, and so we should start to see like a pulse wave here because we only have odd harmonics. And it's kind of what I was expecting. Oh, it's right. It's 1/3, 1/5, 1/7. The amplitudes decrease. The harmonics don't have equal amplitude. So this should look more like a pulse wave. And it does. Right. So basically this is a way of filling a signal with a bunch of harmonics of a fundamental with individually specifiable amplitudes and phases. Yeah, I would appreciate suggestions. I'm kind of new to GitHub. I'm probably not using it optimally. But yeah, I'm open to suggestions. So we can do stuff like 1 divided by 1, 2, 3, 4, 5, 6, 7, 8. Scramble and just have random values between 0 and 2 pi. I am 8. That gives us the first 8 harmonics of a fundamental with sort of random amplitudes and random initial phases. So that can be one way to get to an interesting sort of wavetable. But then I thought, okay, let's add some noise in there. So I just wanted to randomize some of the values. So one thing that I thought I might do is we can say sig.wavefill, and we'll say if, let's see, so 0.5.coin returns true or false half the time, right? True half the time, false half the time. And I think if we do 0.01, this is going to give us false 99% of the time. And we need to pass arguments here, arg x, y, I. If true y equals, no, just y plus random minus 0.5 to 0.5. You return this value, dot fold minus 1, 1, so it stays within the bounds that we want. Otherwise, do nothing to the value. So now we should just see some little random bits of stuff in our, yeah, okay, so that's kind of cool. It kept our wavetable mostly the same, but on each sample, it, you know, did a random choice, and 1% of the time that was true. And if that was true, it adds a random value to that value. And so then we get this. Let me take a look at that real quick, that link. Sync near automatically, get tracking repository. Yeah, I don't totally understand what that is at the moment. I don't know, maybe I could chat with you off stream or something about some strategies for making the stuff I do on stream more accessible on GitHub. Okay, so, you know, if we increase this value, then we get more randomness, you know, and we can also make the randomness not quite so severe, but just sort of gently randomizing parts of the waveform gives us like a sort of jittery thing here. No worries. Okay, yeah, so that's sort of what I did here. But I wanted to very specifically decide, you know, I wanted to have segments of the wavetable randomized instead of just individual samples. And so that's why I created this array here. So we fill an array with between 4 or 7 arrays. And these 4 to 7 arrays are each going to be of size between 5 and 50, and they're all going to contain the integer 1. And then we pad that array with zeros so that the number of things, did I do that right? Well, the goal is that you have total number of numbers altogether is, I think I did this wrong. I don't think this is right. Mod dot flat dot size, because we want the total number of values, zeros and ones, to be 513. So what if I say, so let's just go back here for a second. And if we say mod dot size, yeah, see, that's not right. It's supposed to be 513. So I think if I flatten the array, it's counting the number of arrays rather than the number of ones. So this, yeah, okay. So I did that wrong. I should fix that. Yeah. And then, but it was still working, so I don't know. And maybe Shaper does not necessarily need a wavetable that's power of 2 size. I don't know. Where was I? Here. Right, and then we go through and we say, if the value in mod is 1, randomize the current value. Otherwise, leave it alone. But all the 1s are grouped together in clumps, right? So it's a bunch of 0s and then a clump of 1s. So instead of randomizing a single sample, it randomizes a block of samples. So so we get this sort of thing happening. You can see these have been untouched, and then we get a block of randomization, a block of randomization, a block of randomization, untouched. So I think this time it actually chose 7 blocks of 1s because we have 1, 2, 3, 4, 5, 6, 7 scrambled regions. But if we do it again, now this time it's sort of totally different. We have, looks like 6. 1, 2, 3, 4, 5, 6. And they're a lot shorter. And then the final wavetable was this one. See, I just copied my comment, but that's not correct. So let's take a look at this one. Sort of don't immediately remember what this one is. So we start with an envelope. It just goes from -1 to 1. So, and I need to do my homework. So this should be 513. Right, it's just a linear ramp from -1 to 1. Nothing fancy about that. All right, there it is. Close some of this stuff. And then I have a second signal, which I'm filling with 32 harmonics, the fundamental, and then a bunch of quiet harmonics above that, second, third, fourth, etc. And this one starts 1/4 into its cycle, and then the rest are random. So again, we just have, I'm making a second one here and normalizing it and cutting it in half and adding 0.5, so it puts it in a range of 0 to 1 instead of -1 to 1. And then what I've done is for the first quarter of the signal or the final quarter of the signal, multiply the signals together, otherwise leave them alone. So get rid of some of this extra stuff. I don't really need to do that. Just want to look at it. Yeah. So here we have our linear ramp, and what we've done is we've for the first quarter, we multiplied by the values in the second one, right? And we might as even plot these, right? So let's see, sig.plot, sig2.plot. Let's close some of these windows. Window.close all. Should be doing this. Okay. There goes our scope, but that's fine. Yeah. So here is sig. Here's sig2. Notice that it's got this fundamental, which starts 1/4 through its cycle. So instead of starting at 0, it starts up at 1, and it's got a bunch of higher harmonics mixed in. And then we do our wave fill, and for the first quarter and last quarter, we multiply these values by these values. So we get this sort of thing. And so that's just, and again, I don't really have too much of a plan. I'm just sort of thinking about wavetable wavetables used for wave shaping synthesis that I've seen before, and some that I've seen in textbooks. And I think, how can I make something similar to that? That's just sort of my own creation. And what this does is, if we have a quiet signal like a sine wave or whatever, if its amplitude is 0.5 or less, it only reads through this middle part, and that means it doesn't change, right? That the middle section of this transfer function is the identity transfer function. But as soon as that amplitude gets higher, right? If it goes past 0.5, then we start to distort the wave using wave shaping. Let's look at that in practice here. So now w.plot. Yeah, here's that wavetable, right? It's the identity in the middle and then random stuff at the extremes. So where were we? I think it was this stuff here. So let's take our Sawtooth Wave, and we have to load that into a buffer. And I would like my scope back. Here's that. Here's this. And let me just tidy up a little bit. Yeah. So quiet levels, it's only indexing this part of the wavetable here, right? Because the amplitude is not high enough to get into the extremes. But then, if we go a little further, yeah, then we start to see some distortion. So yeah, the whole reason I decided to investigate wave shaping more seriously was there was something on the SuperCollider forum about making gabber kicks, kick drum sounds, and how to make them sound good, And I've got my simple sine wave kick drum, which is fine, but I was also looking for ways to make it more interesting. And one of the ways is to use wave shaping and filtering in various combinations. Wave shape it, maybe send it through a filter, wave shape it again, back and forth, back and forth. So that's where these synth defs came about. These K-shape guys here, sending it through a shaper, possibly filtering it, and I'm optimistic it'll give me a lot of stuff to play around with, and that's what's going on with. Let's go ahead and quit this and reboot everything. Yeah, this kick shaper pattern, which, oh right, the tempo clock doesn't exist yet, so we'll do this and show some beats. And not working. I just want to hear this again. Hold on. There's that. There's that. Where is it? Okay, that's working. What if I clear it? Now play it. Yeah. So it's picking one of these 4 synth-Fs. And the frequency envelope is fairly random. It's for the 3 values on the frequency envelope could be sort of completely random, or this is sort of like, let's change this a little bit. So the first one here, this is like the completely random setting where the frequency can sweep from like 15K down to 50 in a very short amount of time. So we get lots of like little mouse squeaks and stuff happening here. And then this one in the middle here, it's this. The frequency stays sort of constant through an individual synth. And it picks a random value between 20 and 40, and it copies that value 3 times. And it multiplies it by one of these values to turns it into a harmonic, basically, right? We can multiply by 2 or 3 or 4. So it could go all the way up to 40 times 60, and then it does also detune them a little bit. And then this last one, this is truly constant. It just picks a random value and copies it 3 times. Yeah, within the function. So it's the same random value. And then it sequences through that value once. And so it just, all of these values get the same value. All these keys get the same value. Let's see. Yeah, who was it? Somebody said, I think it was the derf, just turned into a pattern, and it just comes to life. You know, it's all well and good to just play a single synth that's going on some wave shaping thing, even if things are varying. But then string together you know, an infinite sequence of those with randomized values and just I love it. I think it sounds great. I'm really into it. Let's take a look at that one. Good question. Here it is. We have, let me just let that play. If that's annoying, we can turn it off. So we have an envelope. This is an amplitude envelope. We initialize sig to 0, and then we end up summing 4 varsaws together. Each one's got a frequency plus a random noise generator. Yeah, somebody said that at the beginning, actually. I think I must have been subconsciously influenced by that, because I know that track, Confield. It's really good. It starts off with just like these sort of organic sounding metal sounds, and this little 4-note melody comes in at the end, and it's out of nowhere. It's great. It's just, I really like that one. Yeah, so we've got 4 varsaws, each with a unique frequency deviation, random initial phase, random width or duty cycle between provided range. It goes through a low-pass filter, and it's got an envelope on the cutoff frequency. I scale them down because we're going to add them together. So then we have 4 random but similar varsaws summed together. We apply the envelope, we pan it because it's already stereo, so we use balance too. And I run it through a compressor expander. So it's got some, where is it? Thresh. Oh, it's here. Yeah, so it's got a threshold of -6 dB, and the ratio is 8:1. It's 1:8, but the way this unit generator works is it's a compression ratio of 8:1. So it just means I can sort of overdrive it and it won't clip, unless I really overdrive it. And then I have sig equals sig.tan_h, which is something I've seen a while ago and then adopted. Tan_h is hyperbolic tangent function, and it sort of looks like it's let's actually plot it. I think we can do something like 0 pi over 100 2 pi dot collect tan h x a plot. What is your problem? Oh, these need to be parentheses. No, it's, oh, we want to go minus pi to, I am not doing this in the most efficient way. Yeah. Here's a plot of tan h over the domain minus pi to pi, and they're, I guess, asymptotes at -1 and 1. So if you use this at the end of a synthet, basically, no matter how loud something is, positive or negative, it's like a soft clipping function, right? So if we say like we can plot this sine wave here. Right? And if we dot tan h, oh, let's you know, we can multiply this by 10. And hang on, getting all confused here. Okay, so now it looks the same, but it's now an amplitude of plus and minus 10. What if we do dot tan h? It ends up doing a like a soft clipping thing, right? So the range is now -1. Sorry, that's being blocked by the chat. -1 to 1, and it doesn't clip. It stays. It doesn't quite hit 1 or -1 because that's what the tan h function does. It soft clips it basically. So that's what I'm doing in Varsaw perk. Yeah, it is. That's. I think it's Varsaw perk doing the melody. I'm almost positive. Yeah, melody 0. Right. So it's picking from these pitches, and it's sort of triangle wave like. The duty cycle is centered around 0.5, which makes it a triangle wave versus a sawtooth wave. Right, one of these. It's sort of right in the middle. And it's kind of it. Random amplitudes, random panning. So yeah, I think I might call it a day. Neck's starting to hurt again. So I guess I gotta clean this stuff up, and I'll put it on GitHub, and tell D if you want to send me a private message on Twitch or something with that that GitHub link you shared with me. I'll take a look at it. I've got it open in a tab here, and yeah, it'd be good to keep the GitHub repository sort of organized, I guess. Anyway, I hope that was clear, the wave shaping stuff. That makes sense, sort of, about what's actually going on with wave shaping. Cool. Awesome. That's good to hear. It's good when things make sense. Yeah. All right, so I don't know quite what I have planned for next Wednesday. Hopefully something. I think I said this last time, but as the fall semester is approaching, there's just a lot of prep stuff I have to do. And so I may take 1 or 2 weeks off, but I'm teaching a class. I think I may have announced this, not on stream, but somewhere, but I'm teaching an advanced a course on SuperCollider, basically, and I've got a few people registered for it. And the idea is I'm going to actually give the lectures on Twitch, so it's going to be, publicly available. And then the in-class stuff is going to be assignments and workshops and stuff. So once the fall semester starts, it's going to be like very late August. Probably the first official stream for this class will be first week of September. And it's going to be really basic stuff. So we're not going to do this crazy nonsense stuff. Maybe towards the end of the fall semester, we'll get into this, but it's going to be really basic. So maybe some people would be really interested in that, but I don't know. Maybe some people might be not interested, but that's what I'm doing. So we might have 1 or 2 more me messing around with my own projects over the summer streams. And then in September, yeah, I'm going to keep live streaming, but it'll be primarily for my class. And we'll start with the basics and just opening help documents and pressing command period to stop sound. It's gonna be a lot of fun. I'm looking forward to it. I hope it'll be a successful class. And of course, everyone, you know, I hope there's a big group of people watching in class and elsewhere in the world. So yeah, you can get ready for that. It's gonna be a lot of fun. So thanks everyone for watching. I always appreciate everyone stopping in and chatting and asking questions and hanging out. It's a lot of fun. I'm having a lot of fun streaming, and I'll try to figure out something interesting to do a week from today. You know, maybe I'll do a little bit of work off stream and come up with some more textures and patterns, and yeah. Cool. So yeah, thanks again everyone for watching, and I will probably see you next week. And yeah, take it easy.